In the previous video on addition formulae, we looked at how you can prove this using this one and this one. Now you might be wondering to yourself, well, what's the point of these addition formulae? Why would we ever need to expand these brackets here? And I think it's a good question. I think this example here kind of explains the need for using the addition formulae. If you look at the question, we have cos brackets 45 minus theta equals sine 30 plus theta. Now, if what was in the brackets was the same here, we could divide both sides by cos of whatever was in the bracket, and we'd end up with a tan. So if this was 30 plus theta, we could divide both sides by the left hand side, and we'd get 1 equals tan 30 degrees plus theta, which is easy to solve. You did this in year 1 maths, but we can't do that because what's in the brackets is different. So this is why we need to use the addition formulae. We need to use this one here to expand the left hand side, and then we will need to do the top one to expand the right hand side. So if we do that, put all the values into the addition formulae, the left hand side is going to be cos 45 degrees cos theta plus sine 45 sine theta, and the right hand side is going to be, I'm going to run out of space here actually, let's just move this down a bit. So the right hand side would be sine 30 cos theta plus cos 30 sine theta. And now you can just, anything, any time you see a cos with a number there, you can just type that into your calculator. Make sure you're in degrees mode. So typing in all this into your calculator, you should get root 2 over 2 cos theta plus root 2 sine theta. Sorry, this is root 2 over 2 sine theta equals a half cos theta plus root 3 over 2 sine theta. Now I've got lots of fractions there, which is a bit of a pain. So as usual, we want to get rid of the fractions. So we can just multiply everything by 2 to get rid of the fractions. So if we do that, then we've got root 2 cos theta plus root 2 sine theta equals cos theta plus root 3 sine theta. Now we want to get all the coses and the sines on the same side. So if we get all the sines on the left hand side, so if we move this over to here, and if we move this over to here, we can then factorize. So let's just do that. So we'll have root 2 sine theta minus root 3 sine theta equals cos theta minus root 2 cos theta. So then factorize, and we'll have root 2 minus root 3 sine theta equals 1 minus root 2 cos theta. Okay, now if we divide both sides by cos theta, we'll get a tan. So let's do that. So we'll get sine theta over cos theta. We divide both sides by this, and then if we divide both sides by this, we'll get 1 minus root 2 over root 2 minus root 3. So that means that tan theta equals this, and this is very easy to solve now. you can just type inverse tan of all of this into your calculator, and then because it's tan, you can just keep adding on and subtracting 180s until you get all the solutions you need. I think there's only two solutions. The only two solutions I got was 52.5 degrees and minus 127.5 degrees, because the range, if we go back to the question, the range was just between minus 180 and plus 180. Now let's have a look at another example. Here is this is example 6 in the textbook on page 172. It's worth also, before you have a look at this, also have a look at the example on page 171, example 5, where you have to show what sine 15 equals in surd form. You have to prove what sine 15 equals in surd form. That's a good example to do, but it's fairly straightforward how the textbook explains it, so I don't think I need to go through it on here, but do make sure you have a look at example 5 on page 171. So if we concentrate on the next example, then I'm only going to do part C, because if you could do part C, then you should be fine with parts A and B. Excuse me. Okay, so we seem to come across these kind of questions quite a lot in the textbook, whether it's examples or exercise questions. And as I've explained before in previous videos, the way I like to do them is to use right-angled triangles. So let's use this one to find our first triangle. Remember, sine is always the opposite over the hypotenuse. So if we draw a right-angled triangle here, we've got A, the opposite is going to be 3, and the hypotenuse is 5. Using Pythagoras, that's going to be 4. And then if we look over here at cos B, cos is the adjacent over hypotenuse. And so if we sketch this one, we've got an adjacent of 12. I'm just ignoring the negative sign. Don't worry about the signs until later on. So that's 12. This is 13, the hypotenuse. Again, using Pythagoras, that's going to be 5. Okay, so now we can use our right angle triangles to find other ratios. So using the triangle on the left here, we want to get a formula for cos A. We want to get a fraction for what cos A equals. Cos A is the adjacent over hypotenuse, so cos A is going to be 4 over 5, and we'll come back to the sine in a minute. Over here, sine B is the opposite over the hypotenuse, and the opposite is 5, hypotenuse is 13. Now we need to decide what's positive here and what's negative. So if we look at this, A has to be between 180 and 270. This is where I find the cast diagrams very helpful. So if we sketch our cast diagram between, well, this is all 4 quadrants, but all we're actually interested in is the quadrant down here, between 180 and 270. This is 90, this is 0 or 360. But the only thing we're actually interested in here is the quadrant between 180 and 270. Now down here, tan is the only thing that's positive. We already knew that sine was negative, but also cos is going to be negative. Okay, because only tan is positive between 180 and 270 degrees. If we do a similar thing over here, this time the angle B is obtuse. Now, as you know from primary school, obtuse angles are between 90 and 180 degrees, and so the only thing that's going to be positive here is sine. Okay, so that means this will be positive. We can leave that as it is. We already knew that cos was negative. We already know it's minus 12 over 13. So now we could find what tan A and tan B are, but they're just not going to help us for this question because we're only interested in cosec, which is 1 over sine. So we don't really need to worry about tan, although we could work it out if we wanted to. So it might be just worth writing these down now, what all these are before we move on. So I've just done a summary of everything we've done in the green box in the middle of the screen there. So remember in our question, we actually want to find cosec A minus B, which is 1 over sine A minus B. Now the reason it's in this section, this question, is because you need to now use the addition formulae for sine A minus B. So if we do that, that's going to be sine A cos B minus cos A sine B, and then we just whack in all of the stuff in the green box. So it's 1 over sine A is minus 3/5 cos B minus 12 over 13 cos A minus 4 over 5, and sine B is 5 over 13. So if you type that into your calculators, you should get 1 over 56 over 65, and so the answer is just going to be 65 over 56.